Okay, so as we've been going through rotational motion, try to compare and contrast what we're learning now to what we have already learned. We had all those basic kinematics terms, displacement, then we had angular displacement, velocity, angular velocity, acceleration, angular acceleration. We have kinetic energy, which we just went over, sort of 1/2 mv squared, except we made it 1/2 I omega squared. And now torque. And torque relates to force, where we know force is ma. And just as a guess at an upcoming torque formula, if torque relates to force, and force is m times a, what would torque be equal to? Okay, a would be replaced with alpha, but m's replaced not with something else. I. Rotational inertia, moment of inertia. So we will have a torque formula that's I alpha instead of m times a. But we're not starting with that one just yet. Anyway, so torque is the ability of a net force to rotate an object. And depends on, of course, 3 factors. The magnitudes of the forces, if there's more than one. Where these forces are. So you could obviously twist this wrench, but where would it be easier? Yeah, if you grip it at B, you would not need to exert as much force as you would at A. So distance away from the rotation point always matters. And the angle between them. So obviously, this is going to be perpendicular. It would not make sense if you're trying to twist this wrench to be like jerking it off that way or towards the wrench. You'd want to push perpendicular to the rotation axis there. All right, this is also our first cross product, I think. We've done dot product. Remember that? And torque, this is like Greek letter tau. It's like half a pi, kind of. Pi with one less leg. Do you remember what we used dot product for? Yes. Okay, work, which we did force times distance, but they had to be in the same direction. If I was lifting up this crate, okay, I'm lifting it up, the distance is up, the force is up. Those are in the same direction. That would be positive work. Cross products, just the opposite. You do not want those things to be in the same direction. That would not help you rotate it. Again, imagine the wrench is there, you've got your radius here, and then your force, you wouldn't pull along the same direction. That would obviously not cause a rotation. So you want them to be perpendicular. And if they're not perpendicular, you have to break it down into components and find the perpendicular components. Unit would be Newton meters, force, distance would be meters. So like I said, this is the cross product of position cross force. Okay, so we know they need to be perpendicular, and direction is given by the right-hand rule. So let's look back at the right-hand rule just for a second. If something is constantly spinning, this point, how do you describe how this thing is rotating? Well, here it's going that way. There it's going that way. There it's going that way. How do you describe that direction? Well, you could easily tell somebody the direction if they had a right hand and they knew the right-hand rule. The right-hand rule for cross products, you take your hand and you point it along the radius and you curl your fingers towards the force, the direction the force is going. But essentially you are just curling your fingers the way that object is spinning. So here's the bicycle wheel. If I exert this force, this way, okay, obviously I've caused a torque and a rotation. What is the direction of the torque? What? Up. Grip your right hand the way it's spinning. It's spinning this way. So the torque is up. And that way, if you told anybody with a right hand, torque is up, okay, they can take their thumb, point it up, look at their fingers, okay, they get it, it's spinning this way. What if I held it in a different plane altogether and spun it like this? What was my direction of torque there? Very good. Spinning this way, my thumb is really toward you guys. Okay, so that's the right-hand rule. Okay, and then one just quick example problem. With this basic formula, so here's the wrench. It's rotated around a bolt. The distance from the bolt to the end of the wrench is 0.1 meters, where I guess we assume that person is exerting their force. And the force exerted on the end of the wrench is 15 newtons at an angle of 60 degrees. What is the torque? So first of all, what is our torque formula that we just learned? There's more than one torque formula, but the one we just learned, R times F, really R cross F. So is it 0.1 times 15? Not exactly, because we have the angle situation. We can go ahead and take the 0.1, but we don't want to multiply it by 15. You can make components this way and this way. But which component do you want? You want this one or this one? Yeah, you want the sine. So you want 15 sine of 60. Which is no. And this is degrees, so make sure you are in degrees. 13-ish. So a tenth of 13. And stick on your Newton meters as your unit. Piece of cake, right? All right, quick checkpoint, and then we'll go to the lab. Okay, just number 6 on page 253. Says the figure shows an overhead view of a meter stick that can pivot about the dot at the position marked 20 for 20 centimeters. All 5 horizontal forces on the stick have the same magnitude. Rank those forces according to the magnitude of the torque they produce greatest first. So let me start you off with which 2 would provide 0 torque? So it's R cross F. F2 is correct. F2 is definitely 0 because there is no R. That would be 0. And F5 would also not provide a torque. I mean, sure, it's a force, but that's not going to cause a rotation. So F2 and F5 are 0. So then out of 1, 3, and 4, what would cause the most torque? Okay. 1 actually ties what else? 3. And then 4, because the perpendicular component of 4 would have to be a little bit less than 3 or 1. But notice it doesn't matter what side of the pivot it's on. I mean, F1 and F3 would provide the same torque. But F4 would have as force. It's the force causing an angular acceleration. So often it's taking something that's not moving at all and making it spin. All right, last class, we learned one of our equations for torque, R cross F. Realizing that, again, the force does not just have to be one force. It could be many forces acting on something that's trying to make it rotate. Or like the whole problem we just went over, you know, if you have a irregular shaped object, you could have different radii and different forces corresponding to each radii. So you may have to sum that all up. But what we also know about torque is, of course, it is the rotational analog to force. So where force causes a mass to accelerate in a straight line, linearly, is that a word? It is now. Torque will cause something to rotate with angular acceleration. So we already know what the formula should be just based off of what M and A are in the rotational world. What's the mass correspondent in the rotational world? More than just mass. Wes, you're all right. Oh, we're gonna cut. Okay, take 2. We talked about this yesterday. All right, how about this one? We have tangential acceleration, or just linear acceleration here. What is the rotational corresponding variable? Alpha, okay. So we're just going to swap that and that. But M, it's not just M anymore, it's I, thank you. Because mass is, of course, inertia. Resistance to change of motion is based solely on mass. But resistance to rotational motion is based on more than just mass, but where that mass is. So that's usually mr squared for like our point masses. Okay, so now simply proving this, we have our little marching band equation. Linear acceleration is equal to alpha times r. And we're going to plug in here. But what is mr squared? Inertia. That is the moment of inertia, as long as we're talking about a point mass. So anyway, this is the formula, the other formula you need to know. And we will spend, a little bit of time combining these two formulas, cross force and then I alpha, since they both equal torque. All right, real quick to 253. Lucky winner is Tyler. All right, figure 7, bottom right there. So the figure shows an overhead view of a meter stick that can pivot about the point indicated, which is to the left of the stick's midpoint. 2 horizontal forces, F1 and F2, are applied to the stick. Only F1 is shown. F2 is perpendicular to the stick and is applied at the right end. If the stick is not to turn, what should be the direction of F2? Up or down? Here's our sort of meter stick. So our rotation point's like right here. Yeah, if you already have one force down on this side, well, that's going to make it want to rotate this way, so you need a force to oppose that. So it'd have to be down. Should F2, the magnitude there, be greater than, less than, or equal to F1? If it's not going to rotate, the torque should be equal. This torque, trying to make it rotate this way, should be canceled out by this torque, trying to make it rotate the other way. So it's R cross F, that should be the same. So this has little r, whatever, medium F. But this side has big R. So F should be smaller, because it's the product that needs to be the same. Like on a seesaw. You can space your people out accordingly so that you're always balanced on the seesaw based on how far away they are from the pivot point. You know, so if you've got like a big person here, you got your adult here and your kid, put your adult sort of in the middle of the seesaw, where would the kid balance out the adult on the other end?
The adult's in the middle and the kid's on
the adult's in the middle of his side, pivot point's in the middle. Would the kid need to be close to the pivot or farther away?
farther away.
Yeah, definitely farther away. Smaller force, smaller weight, but bigger R. Okay, so now let's do one example problem. I'm done with the notes, but you'll need a little bit of space to do this. So here's sort of a typical force problem, or a torque problem, I should say, where we use the two torque equations we know. So we have a pulley, and here's how you know pulley information matters. A lot of the time they'll say it's a massless pulley. Well, they gave you the mass of the pulley. And they went out of their way to tell you it's a disk, which should make you think what? Yeah, the formula's from that page in the book. The moment of inertia for a disk, which would be 1/2 mr squared. No, not the hoop. This is going to be a solid, sort of solid object. We're assuming it's a disk, and that would be like error if this were a lab. It's just not truly a disk, but we'll call it a disk. Okay, so we know information about the disk. It's mounted on a fixed horizontal axle. A block whose mass is 1.2 kilograms hangs from a massless cord that's wrapped around the rim of the disk. Find the acceleration of the following block. The cord doesn't slip and there's no friction at the axle. All right, so first, hint number one, draw a free body diagram for the hanging mass. Okay, so here's our hanging mass. What forces are acting on it? Tension up and weight down. Would I say tension equals weight?
Well, no, because the pulley has a mass. Or
No, but that's not why. Yeah, it is accelerating down. In fact, we are trying to find acceleration. So when we had an accelerated situation, what was the formula we used to write? What? That one? Well, we find our net force, which would really be due to what, mainly? Weight minus tension. What does net force equal? That's Newton's second law. MA. So we would typically write something like that. So that's part of our solution that we will need. Right, but I don't know what T is. If I knew the tension in the cord, I would be done. I wouldn't need to know anything about rotation. I could solve it as is. But I don't. And as a guess, how would we know we were wrong? Like, what is a clearly wrong answer for the acceleration of the block?
if it was negative or if it were positive.
Well, aside from the sign, how is the magnitude?
It was getting smaller. It was higher than the gravity.
It is bigger than gravity. It can't possibly be going faster than free fall, because we do have this force holding it back a little bit. So that's at least one clue that we may have done it wrong. Hopefully we won't get an answer bigger than gravity. All right, so we've done what we can with forces. Now let's look at rotational stuff. And I'm going to give myself some room, not with the eraser. Now I'm going to need some numbers from you guys. Not your favorite numbers. Okay, a torque diagram, and I guess both of these are really drawn already for us. Sort of like a cross-sectional view of your thing that's rotating. And it's where you would simply show the forces that are acting on it. So what is making this pulley rotate? indirectly due to the block, but specifically what name of what force? Yeah, it is a tension. That is the force causing it to rotate. And it's acting right here. This is where it is pulling. And of course we know the radius of our disk, so we can get the torque there, but of course again the problem is we don't know tension. So setting up what we do know about torque, we've got our two equations, R cross F, and the one we just learned, I alpha. I'm going to start plugging in there. Do I know the radius of this thing? I hope so. I just erased it, but.
Yes, 20 centimeters.
20 centimeters, so I'm going to make it what? 0.2. All right, now, what force do I plug in?
Weight.
More than weight. The weight is...
10th grade, please report in the auditorium. 10th grade.
The weight is not making it rotate.
The auditorium.
I mean, indirectly, but it's the tension. The tension is...
Austin Galloway, report to the main office. Austin Galloway, report to the main office.
She's waiting for you to talk to cut you.
I know. The tension is the force providing the torque. So I need to plug in tension here, which I can rearrange from this equation. So add that to the other side and that around. So
Wait. Why could the tension equations be the same though? Because it's two different maths. I don't see how that's
how can I relate?
this.
I mean, yeah, it is two different masses, this mass and this mass.
Tension?
No, because it's the same chord. You know, there's nothing else in between this point and this point. The tension of the string should not be different here versus here. It's got to be the same. Okay, so this is tension. But you are right that we do need to pay attention to what mass we are talking about. This tension formula came from the mass of the block. So let's take the time to plug in those values so we don't confuse ourselves in a moment. What was the mass of this block? Okay, so that's going to be do I know what A is? No. That's what I'm trying to find. All right, now I want to set this all equal to I times alpha. Okay, so we knew our I formula was 1/2 mr squared. That's for a disk. Look that up. So plugging in relevant disk information. What was the mass of the pulley? Kilograms? Okay. And you said the radius was 0.2? Yeah, but how do I deal with alpha? Do I know anything about radians per second squared? No. But look at the slide previous to this. What is a formula that relates? Not MA.
Well, A divided by R.
Yes. We had our little marching band equation. So we got to pull that one in too, because I don't know anything about alpha, radians per second squared. And I wanted to find A anyway. So if I divide by R, that should be set up. So it makes for a lovely long equation. And you got to be a little careful because you got A in two spots. I will let you guys do the math magic. And I will check my answer. You know what you get.
So 1 half m squared is
Please come to the main office.
Which is less than gravity, so we are hopeful that we are correct. One more time, a quick recap of this. When you're doing torque problems, you often want to set torque equations you know equal to each other. To get rid of alpha, use your little marching band equation and plug in A over R. That will get rid of alpha for you. And then everything is in terms of linear stuff.
Would you combine the two?
Yeah, at some point you'd have to combine them.